Hi, everybody. Welcome to this ADAS webinar, using satellite Earth observation to improve or streamline agricultural processes, which we're running for AgriTech Week. It's wonderful to have you all with us. My name is Brie Cooney. I am the marketing manager for ADAS. I'm first going to run through some general housekeeping, and then we're going to have a brief introduction to AgriTech Week by the organizer AgriTech E, who will share what the week's about and share what else is happening. Then we'll pass over to my colleague Ben Hockridge, who will lead us into the presentations. So housekeeping. Let me just get my slide. Right. So you may have noticed coming into the webinar that your cameras and microphones are automatically switched off, a standard procedure for webinars these days. For those of you who've registered but maybe cannot be with us today, we are recording this session. The recording will be sent around to everyone afterwards to watch back. You hopefully have a button at the top of your screen that is a Q&A button, so that purple icon there with the chat bubbles. We will have a Q&A session at the end after the presentations. Feel free to enter your questions as you have them into the Q&A chat, and I'll read them out at the end to the presenters. You can also upvote. So if someone asks a particularly good question that you also want to know the answer to, you can hover over the question and use the up arrow to vote for it, and we'll ensure that we answer it. If you would rather ask your question to the presenters directly, raise your hand, use the icon there with the hand, so I know to give you mic access, and that will allow you to unmute yourself, and then you can ask them your question. Right, I believe that's all the formalities out of the way. So over to Thomas at AgriTech E to tell you about AgriTech Week.
Hi, thank you very much, Brid. I'm Thomas Wedd. I'm membership manager for AgriTech E. And welcome everyone, and thank you very much to ADAS and the others for hosting this. And so if I just explain what AgriTech Week is, it's our partnership program to help celebrate and bring together communities across the AgriTech ecosystem. This is now our 11th year, and it's the biggest one we've ever had, with this being the 5th event of the week. So we've had some other events, including an event today put on by BASF, and we've had one at Bagram Institute by Bug Biome, and lots going on, and we've got a few more. So tomorrow is our REAP conference, which is our annual conference at Newmarket Racecourse, and there are still spaces available if anyone would like to go. If it's all right with Brid, I'll put our web address in the chat, and also my email address. And so AgriTech, we're a not-for-profit independent membership organisation. We exist to bring together the communities of farmers and growers, tech developers and researchers, and technical and professional service providers. We do have a sort of vibrant calendar of activities, of which AgriTech Week is one. And AgriTech Week is delivered by our members and we curate it. So there are 9 events in total. And I'd be happy to talk about AgriTech E membership. I'll put my email address in the chat if anyone's interested. And we'll be sharing the event proceedings for the whole of AgriTech Week on our website next week. And yeah, so it just really remains to say a big thank you to Brid, Ben, Geoff and Andy for putting on today. And we wouldn't have an AgriTech Week if it wasn't for members such as ADAS. So yes, and we're very proud to have them as members. Thank you. Thank you very much. Over and back to you, Brid.
Okay.
Thanks,
Thomas. All right, I'll take over now and share my screen. Hey, can you see that all right? Okay, so yeah, welcome everyone. So we've got 3 talks this afternoon, all looking into how satellite Earth observation can be used to improve or streamline agricultural processes. And the idea of these is to give you a flavor of how the data from the array of sensors now orbiting our planet can be applied in the agricultural sector. So the three talks we have is, first of all, by myself. I'm Ben Hockridge. I lead the geospatial team at ADAS, and I'll be talking about the use of satellite imagery to predict yield in vining peas. Then we have Andy Shaw with Assimila, who will be demystifying satellite imaging, making remote sensing useful to farmers. And then we have Geoff Smith with Specto Natura, introducing EU Grassland Watch, which uses satellite data to explore the evolution of grassland. So I'm going to make a start on a project we've been working on that we've named PSAT, and this started November last year, 2023, and this has been funded by the European Space Agency and carried out in partnership with HMC, who are a pea grower cooperative. And yeah, as I said, looking at satellite imagery to predict yield in vining peas. So starting off with the challenge. So with vining peas, there's a small window, typically sort of 1 or 2 days, when the vining pea crop is fit for harvest. Following harvest, the crop must be processed within 2.5 hours for freezing or 4 hours for canning. If it can't be harvested and processed within that time, then it's bypassed. And some of that bypass crop can be harvested for livestock or seed at a reduced value, but a significant proportion can be completely wasted. So vining pea growers work with processors to try and manage a continuous and even supply of peas into the processing factories. However, the grower groups often budget for a proportion of bypassed crop. So the HMC group, who we work with, budget for around 7% of crop to be bypassed each year. So this challenge represents a good market opportunity and one which this project aimed to address through reducing that proportion of bypassed crop. So how do we address this? Well, processors need an even supply of crop to the factory, so it allows them to prepare and open lines ready for processing larger volumes, or even close down some of the lines when lower volumes are expected. So to do this, they use sort of planning schedules and grow different varieties to manage a consistent intake. They can also manage the supply in 2 other ways. So first of all, forecasting the harvest date. So HMC have developed a harvest date model based on weather data to estimate the timing of harvest. And the second is forecasting the harvest volumes. So that's the area that this project aims to address, this need for yield prediction, and see if satellite data can be used to do this. So within the project, we started off with the data collection exercise. So HMC provided us with field information for 5 years from 2019 to 2023, providing field boundaries, variety, dates of activity, and yield. Then we also brought in weather data. So this is used to calculate heat units, which I'll talk about in a second, and that can be used as a proxy for crop maturity. And then finally, satellite data, which is used in calculating a range of vegetation indices, which we're then able to use to explore those relationships with yield. So I mentioned heat units. So this is a graph of temperature over the season in 2023, and the purple line shows those accumulated heat units. And a heat unit is the number of degrees above 4.4 degrees Celsius. And different vining pea varieties have different requirements or targets for heat units before they can be harvested. So in an example here, one variety called Tomahawk has a target accumulated heat units of 630. So if it's planted in April, then it accrues those 630 heat units and then is harvested sort of 80 days later. And by using this measure of how many heat units it's accumulated, we can get to understand how mature the crop is. Once we've got this information for all of the crops and fields that we have the data for, we were able to look at satellite imagery available within that growth window. So carrying out an extensive imagery search of Sentinel-2 data for each field and identifying the crop maturity at the time of the imagery, and then calculating a range of vegetation indices. This was then used to look at the relationship between those vegetation indices and final yield through the season. So here we have a graph of that relationship and how that correlation changes over time. So this uses here we've got the optimized soil adjusted vegetation index and shows how the correlation or R squared of the relationship changes with the 20-day moving window and how that changes based on the maturity of the crop. So we have that strongest relationship at around 60 to 90% of crop maturity. However, this only incorporates sort of 40% of fields that have a cloud-free image within that time frame. However, if we extend to sort of 40 to 90%, the number of fields where imagery is captured extends to nearly 70%. So in this, we looked at sort of both of those timeframes to develop models for. As well as looking at this over time, we also considered how the year or the variety affected these relationships. And there were considerable differences in which vegetation index performs the best with different varieties. Therefore, we needed to consider a number of different vegetation indices, the timing through the year, and therefore to consider all of these variables, we made use of machine learning to consider all of these different factors. So in developing the model, there's a whole range of different machine learning models available for analyzing the data. So we gathered all of the data together, filtered it based on its sort of maturity through the year. So in this case, sort of filtered to those where we had data for 60 to 90% crop maturity. Split the data sort of with 80% for training, 20% for testing, and then experimented with different variables to see how the model performance changed, and then ran this sort of multiple times, and the box plots show the results of this. So this model was trained and tested with 330 different data points, with linear regression forming the best with sort of an R squared of 0.73, but showing quite a bit of variability. So the model that we actually took forward was the random forest, performing with a correlation of 0.71. So that was using the 5 years we had data for. It meant that through the 2024 season, we were able to use those models that we had developed and test it on that season. So as imagery became available, we were able to run the model and provide a yield prediction. So it wasn't a great year for satellite imagery, but we collected 2 cloud-free images, one in June and one in July. And so this graph shows the best prediction of yield from the PSAP model plotted against the weighbridge yield from the harvested crop, with the 1-to-1 represented by the dotted black line. And so this has predicted the final yield pretty well, with an R squared of 0.71. And especially when you consider that in some cases yield prediction has been carried out just using a standard yield depending on variety, and so it performs very well in that case. That said, we were only able to produce a prediction for less than 50% of the fields. So another part of the study also looked at using other imagery to sort of fill those gaps, and sort of performed similarly in terms of sort of that correlation as well. So yeah, as a sort of wrap up, we were able to help estimate crop volumes coming into the factories. The data can also be used for looking at subfield variation in crop yields. Here's a quick example just with the imagery on the left, and then the sort of combine data on the right hand side, which is interpolated. So the bottom two images, one the sort of on the right, the sort of real data, and then the left, the satellite imagery, so we can look at those relationships. And then the idea going forward is to develop a user interface and live system, which will be used to better improve those communications of that data between the grower groups and the processors, and ultimately take the development of the model further using other sensors and other weather data as well. Thank you very much for listening. I'll stop sharing my screen now, and I'll pass over to Andy.
Hello there, sorry about that. I think I've shared my screen without turning off my mic and camera. Can you see my slides now?
Yeah.
Because I can't.
Okay.
I can't see my slides anymore. Hang on one second, I'm just going to stop and then do it again so I can see what I'm talking to. There we go. All right, I'm good. Okay, thank you, Ben. There we go, lovely. Sorry about that. Hi, everyone. My name's Andy Shaw. I'm a director of a company in Reading called Assimila. We're an Earth observation science and applications company specialising in the science of satellite Earth observation. And for the last few years, we've been developing applications of remote sensing for agriculture, which cover mainly arable crop analytics, but we've delved into pest and disease risk forecasting, grassland monitoring and other things. And I'll show you a few examples of that as we go. Let me just get my slides moving for you. So I was just thinking about this meeting and thinking I obviously want to tell you about what we can do in agriculture and processes and streamlining, but I'm aware that the modern landscape for farming is changing, and I want to get people thinking about how when you see those images of Earth, there's more information there than you need for one application, and we can adapt that for different types of application. I've mentioned arable farming and pest disease management, but we've got a lot of talk now about carbon. Do we know how much carbon is on the farm, how that's changing? Do we know about what nature and biodiversity we have? And I understand all the pressures that farmers are under. I wouldn't want to be doing it myself, especially after the budget. Remote sensing can feed into a lot of these areas, but I think it's hampered by a lot of complexity, accessibility, knowing where to find this information. Do you need to have a PhD in remote sensing to make use of this stuff? Making it usable, for us, the point about usability is it's one thing having an image and turning it into some sort of metric, but how do you link that to a decision point? So we've worked hard to try and use data in a modeling context that we can provide information at the point in time at which a grower or someone needs to know that information, which is why you'll hear a lot about the use of modeling as well, which is something I think that sets us apart from many remote sensing approaches. We don't just use data, we use models as well. And the use of models helps us improve reliability. Of course, if you have a very cloudy season, as you just saw in the images already, you get a lot of cloud in England, funnily enough. And that's one of our biggest bugbears, but we've dealt with that now, and we know how to remove those clouds, to gap fill and create long time series with that in mind. And we've tried to provide tools and services that take all that complexity out so that you can just get information that's reliable. So we try to produce trust in this kind of data. I'm aware that in the past people have tried this kind of technology and it's been found a bit wanting for one or more of the above reasons. So our solution, what we're trying to do is to develop a kind of a multi-purpose farm and agriculture information service, which for the purposes of today, I'm trying to think about its scalability so we can operate and provide data at a field scale. So if you're talking, like you've just seen, a field of wheat or grass, but because remote sensing covers the whole of the country, how can we do that at country scale so that we can do things like comparing field to field or region to region, do top-down analysis and top-down statistics as well as that kind of field upwards. We want to make it timeless, so hence the use of modelling so that we can run models backwards and forwards. It's a bit like I'm looking out at the weather now, it's cloudy, what's the temperature going to be, when's it going to rain? We copy the techniques of modern weather forecasting so that we can project into the future, but also make better, get better understanding of history in the past. So you'll hear us me talk about models. And it's that combination of models and data and agronomic intelligence. And we've had the pleasure of working with the likes of ADAS and the various universities in the past. And I'll talk about later a project to bring all this to life that we're in at the moment called NUE Profits, about nitrogen use efficiency, which I think will be of interest to some of the attendees on this call who aren't necessarily involved in the growing, but are interested in how do we manage our emissions, how do we reduce the impact on the environment and nitrate runoff and that kind of thing. Back to this problem of it's a multi-dimensional problem. So what I'm going to do now is just give you one slide of science and then show you some examples. It's going to be a bit of a rush through and then get to this example of nitrogen use efficiency. So this image, I'm sorry, it's a bit sciencey, but I'm trying to get across the point that we're not just about images anymore. We're trying to take data, measurements from those imagery about different crop parameters, combining that with data about the soil, about meteorology, and then we use that to calibrate and run models. And we use a process called data assimilation, and it's what is done in modern weather forecasting. And it means the models and the observations work together to get a better analysis of what the data is you need, whether that's at sowing stage, emergence stage, anthesis stage, or whenever. Obviously, the remote sensing gives us more information as the crop grows, as the canopy develops. But we can say things with models even without that data because we can drive them with meteorological data in their absence. So we use those together and we get multiple outputs. It can be crop data, it can be a forward yield estimate, it can be analysis of how things might be how the crop is developing, whether there's pest and disease. And to refer to the other issues I mentioned, we soon will be starting to turn this into carbon and biomass calculations. And we can start generating things like habitat, extent and condition from the same kind of data, the same kind of approach. So eventually we should get to the point where we can offer you as farmers or growers or anyone interested in the farm supply system, multiple information sources related to the practice of farming and land management. So this is the kind of thing you get. I hope you can see this. This is kind of something that you've seen Ben showing, but in a sort of video form. You can see in the bottom right there the problem with the clouds. You're trying to look at your field, but the clouds get in the way. So we run the model, we bring in the data when the clouds aren't there, we treat the data so it's as high quality as we can get it, and then we produce what we call a biophysical parameter. We try not to use the indices that have been mentioned because they're unitless. They don't really relate to a physical property of the crop. The one you see here is called leaf area index, or it's called green area index in this chart. And that is an actual measure of the number of leaves on the plant. So you can get some idea of biomass. We can generate other products such as chlorophyll, the amount of light being attenuated by the crop, and they give us clues as to how the plant is growing and developing. But this one graphic shows you how we develop that through time. And by having that through time, you can do the year-on-year comparison. So maybe years when you have the same rotation, how are things developing compared to before? What are the reasons for the changes in performance? How things are going? And of course, if you're someone who's never farmed that land before, it'd be helpful for you to have that historic comparison. Also on this slide deck is the idea of a yield forecast or estimate. And as we go through the season, we can start providing early forecasts. The example here is from April onwards. That's generally the period after which the crop is starting to develop and show. and we make early estimates. And as the season moves towards the end, you get more accurate forecasts with a reduced error. And that's one of the benefits of using the modelling as well. We can generate errors and uncertainties about our forecasts. They are never perfect, and don't believe anyone who tells you they can get a perfect forecast. I'm sure you wouldn't believe them anyway. But we've got a method where we can show you how we generate those statistics, and we can give you a measure of uncertainty, which we find that people like. It's just being honest about the uncertainties in the data. And as long as we are honest about that, then we can make judgments on the basis of that forecast, knowing how uncertain it is. In the same way that currently economists would use estimates of the national GDP, it's always uncertain, it's always fraught with error, but we still use it because we understand how the models work. So that's what we're trying to move towards. This graph just shows you a variety of other what we call physical parameters. So leaf area index is the top one, but you have things like fractional cover, how much the canopy of a crop is developing. FA-PAR is about how much light is being utilized by the crop, and chlorophyll, which is linked obviously to the health of the crop and how much green matter is generating. You can see they all show something different. And I think that over time, we'll learn how to use these parameters together to get a more holistic understanding of how our crops are developing and what the problems might be. So if you're seeing fewer leaves or more leaves, and the chlorophyll is high or low, it might indicate pest or disease damage and that kind of thing. So that's what we're trying to get towards. And the shady areas here are understandings of uncertainty in that data. So it's a variety of time series we can generate for the fields using this approach. I've shown you leaf area index for a typical wheat crop. This example I'm showing you now is for a potato canopy cover. So the F cover example, this was used to provide data to a potato modelling company who couldn't get the farmers to go out and do, well, how much is the canopy developed? You have to go into the field often, and it's something that farmers don't want to do. They just don't have time. And we found a way of using remote sensing to get that estimate through quite a short growing period. So again, you can see this multi-temporal through time with uncertainties, and that's a system that was running operationally across the country. This example, this is a very difficult thing to do, grass biomass, and there are a few people starting to put products on the market for doing this. And we're doing the same. We worked with Newcastle University to verify with quite sparse measurements in field. There's not a lot of ground data out there. So if you have data about grass biomass from SPAD meters or the like, we'd be interested to talk to you because I think we can improve these models. But what you see here is across a whole farm and in the different fields, the level of grass biomass in each field as you go through a season, which can inform the production of silage or grazing for the cattle, but in a holistic farming context. So same sort of thing. So different products. Now, if you then take a step back, if you take the bird's eye view of the country, this kind of example becomes feasible using those techniques, comparing data from one field to another. And this is really ideas that we've worked on with our friends at ADAS and the Yield Enhancement Network, where looking at comparisons of performance by aggregating data across many fields, anonymizing the data, and then placing your field back onto that graph, seeing how's my yield compared to everyone else's, or it could be your LAI, it could be your chlorophyll levels, whatever you like. But it gives a farmer a way of seeing how am I doing, how do I compare to others in the region? And more analytics can be derived from this. We might start seeing areas of the country or farms or fields that are consistently underperforming, and maybe they should be prioritized for alternative land uses. So that's a kind of a step back and one of the benefits of the satellite observation capability. So that was a quick run through about some of the things we can do with the approach that we take. And I just want to finish now with one example of a project we're working on. And again, it brings together this idea of crop analytics and production and yield forecasting, but really with the view with a triple bottom line, as they call it. So clearly farmers, and this project started when the energy crisis was occurring because of the invasion of Ukraine. So energy prices were sky high. We know that nitrogen production, fertilizer production is energy intensive. So it was very, very expensive. I think things have settled down a bit, but still fertilizer inputs are still very expensive. But they have a serious negative environmental impact through greenhouse gas emissions and leaching and nitrates in our water systems. So the question was, how can we help farmers be more efficient with their application of nitrogen? And our colleagues are ag analysts who are specialists in this. They're farming experts. We're not the farming experts. Think we can get the current average nitrogen use efficiency up from around 60% up to about 80%. And that difference can mean hundreds of pounds saved in nitrogen-based fertilizers that maybe you don't need to apply. You can save money, reduce emissions, and reduce environmental impact. So that was the challenge. And our role in this was to use our modeling and observation technology to help understand the current levels of nitrogen in your crop. It's actually a multi-technology approach. We have partners who are looking at soil nitrogen, partners looking at leaf nitrogen close up, but you can't do that everywhere all the time. It would be too expensive to go out into every field all the time. So we use the remote sensing to scale that up to say what is the nitrogen content at field scale across large areas. And we're testing that right now. We're in the second year of our project, and we test that against sensor nitrogen values from the likes of Yara and others. And we're seeing good correlation between our leaf area index data and soil and sensor nitrogen data. So we're getting quite confident that we can tell you something about the nitrogen level in your crop. And if we can provide you that at the right time in the growing season, it will help inform a decision about, do I need to apply more nitrogen or not? At the same time, if you can provide a yield forecast, it might also hammer home the point. If you're looking like you're going to get a good yield this year, again, why would you need to apply more nitrogen? If your soil leaf nitrogen is good enough, the crop's developing well, the forecast is looking, with an 80% confidence level at being a pretty good year, again, it might confirm the need to use less nitrogen and get all those benefits of reduced emissions and impacts. And in this project, we're working with ag analysts and other partners to then produce a dashboard like the one you see here. If you go to the ag analyst website, you can see an example of where the farmer in this field saved hundreds of pounds on fertilizer costs at 2021 prices compared to 2019 prices. We're still developing this methodology and testing it as we go. It's not it doesn't work equally well everywhere, partly because of the lack of other data inputs on local soil conditions and weather conditions, but that's what the project's working out. And we hope to have a system going in the next couple of years that anyone could get access to and get those triple line benefits, saving money on your inputs, reducing your greenhouse gas emissions, and contributing to the NFU net zero targets, and reducing those runoff impacts for which we know water quality is highly related to agricultural production, again, which varies across the country. But that's our example. We are exhibiting at REAP tomorrow. So after this session, I'm going off to Newmarket to meet everyone there. So if you're at the conference, I look forward to seeing you, and come to our stand. We have a stand and we can show you more of the data that I've been talking about. Okay, thanks very much.
Okay, hello everybody. Thanks Andy and Ben for introducing the topic. Let me just get my slides rolling. Okay. Okay, can you see those in presenter mode?
Yep, that's fine, Geoff.
Okay, great, thanks. Well, hello everybody. I'm going to talk about what's possibly the next step in the process from what Ben and Andy have been talking about. And I'll be using an example of monitoring protected sites, but that's not the key topic I really want to talk about. It's more about an exemplar service to show how all this information, all these models, etc., that Andy's been talking about, can actually then be built into a service that can be run operationally and scaled over large areas. So I'm going to talk about EU Grassland Watch, which is a European Union service, and it's been built on what's known as Copernicus data. So these are Sentinel satellite data sets, but also something called the Copernicus Land Monitoring Service, which are layers of information which are generated regularly and operationally, which can then be exploited by end users. The project is built by a large consortium. I'm only a very small part of that. So all those logos and names at the bottom are all responsible for what I'll be discussing now. So just very quickly then, why did we target grasslands in protected areas? They obviously have high biodiversity value, and they are also under threat from from things like climate change, land use change, etc., intensification and extensification of management. And when the EU last did a survey of the condition of these grasslands, they found that just under half of those were in good condition. but they also found that 35% of them were also of unknown conditions. So the amount of information that has been collected for these grasslands in these protected sites wasn't good enough, and so there was therefore a need for a service that would identify things like land cover changes and these processes such as intensification and extensification, and help to support the Habitat Directive reporting. So in this way, we can then help member states or other organisations to then report on what's happening in their area or their protected site. So to go back to the objectives of EU Grassland Watch, and I think this is where we then now start to think about how this kind of approach can be applied more generally. The first thing is to have an operational service. We have lots of projects in Earth observation, but very few of them then continue on to become operational services, which are sustainable over decades. And so that's one of the key aspects of this work. We want to deliver information quickly and in a suitable time frame for people to then take action. As I said, we need to look at the status and changes within these sites. We focused on Natura 2000 sites, which is a European protected site designation, and we selected out the ones that were dominated by grassland. And the final thing we wanted was to actually go back in time. So the Natura 2000 designation started to appear in the early 1990s. So what we wanted was a long time series of information so people could see how their sites had changed over time. And obviously, you know, this, as I said, the same processes could then be provided for other environments, not just grassland. Unfortunately, we had a precursor project called COP for N2K, and that had already built a prototype service that we could then exploit and expand. And just to sort of summarize what we were kind of really hoping to gain. So this is a Natura 2000 site here in the blue line, if you can see that. And what we wanted was regular maps of this area, mapping the land cover and grassland types in this region. And we update those as regularly as possible, preferably every year. And then from those maps, we wanted to automatically summarize important indicator information. So here we have a plot of total area of grassland and how that's changed over time. And on the right-hand side there, we have some plots showing how the distribution of different land cover types has changed. What, as grassland has gone down, what's it been replaced by? So to kind of summarize where we are at the moment, I'm just going to do a quick on-screen run through of what would happen if you then logged into the current version of EU Grassland Watch. As you can see in red there, it says prototype, and there's an orange banner saying that it's currently under development, and so not all the functionality will work. But if you can read that URL at the top there, or if you just Google for EU Grassland Watch, it will take you to this web page, and you can try it out for yourselves. So if you then scroll down the web page, so we're still on the front page here, there's lots of information about the service, but all you need to do then is to hit Start Exploring, and that then immediately takes you to a map view where all of the Natura 2000 sites that we've mapped are highlighted. And in this prototype version, we have about 3,600 sites, but in the final version, which we're developing now, that will increase to about 16,000 sites or just over. And you can see here these sites are coloured up by the amount of grassland they have within them, and we can then quickly just click on one to begin exploring it. And that takes us to this site-based view. So you can see this is quite a large region somewhere in France. The dark greens are woodland, the lighter greens are grasslands. And so you can see here we have a very complicated matrix of different land cover types all mixed in together. And on the left hand side, you can see there what we have different levels of information you can report, and also there's a little tag saying added value products. And so if we do a zoom in but also expand that set of products here, we can see that there's various grassland biophysics, grassland phenology, like Andy was saying, getting away from these Earth observation technical terms to more terms related to the land management, etc., grassland mowing events, bare soil occurrences, etc. So behind this product here, we then have lots of information that can be extracted. The little graph you could see on the very left-hand side there, I won't show it, but it will then give access to a lot of indicators, those plots of changing grassland amount over time, etc. But one of the important things to look at here is the bottom line here, where you can see that kind of a line with sets of dates, and each one of those dots represents a different map. So we can actually go back right the way to 1994 and then track forwards, seeing how the area has changed over time. And you can even do a little video. So it's, you know, it's very quite very intuitive, and it really shows up the changes that are happening there. But the key thing that we're changing for this next version is to we're actually moving to, rather than classification, we're moving to a grassland description. So this is a way of providing more information for each parcel of grassland or pixel of grassland that is present in our site. And another key message here is that there's a huge amount of information sitting behind this product. So we have satellite imagery, various geospatial data products, and even things like digital elevation models sit behind it. And we use all those different layers in an analysis procedure to generate these categories of outputs that we see down the right hand side there. So we have basic land cover, which you're all familiar with: forest, water, agriculture, etc. And then we go through the different grassland types, so subdividing the grasslands. And then we have grassland management types, so different management processes and regimes. And then finally, grassland productivity. So like Ben and Andy was saying, it gives us an indication of the yield or the productivity of the grassland over time. And so the final example here is just to say, if we did have a particular grassland type, such as natural grassland, then we would actually be able to make it up by looking at the permanently herbaceous areas within the maps. And it may be a dry grassland, and it may have permanent or no management activity going on there. It could have extensive management, and then it might have a stable productivity. But this means is these properties can all change and be interrelated. So that gives us more of a clue of what's happening to the land surface. It may stay as natural grassland, but we might find that its productivity, for instance, turns then to be degrading. So that's then a reason to do some management activity. I realise I'm running out of time, but I'll just quickly run through the conclusions here. So the idea of the grassland monitoring as a use case for Earth observation has been around for a long time. People have often thought that this is something that it should be doing, but a problem really is that the need to have access to huge amounts of data, lots of imagery, especially if you're working over large areas. And so this is a real challenge. Users are put off by this challenge, and we find that to make a service successful, we need to be able to map at continental levels, but we need to be able to give detail down to local scales. So the EU Grassland Watch service has tried to exploit this huge amount of data that's now available within Earth observation and within geospatial products. We do all the heavy lifting in the back office. So as a user, you don't need to see the imagery yourself or analyze it yourself. And then we've combined that with an intuitive front end that within a few clicks you can actually get through to actionable information for your site. So what we're finally doing is we're not really promoting this as an EO service. We're promoting it more as an environmental monitoring service or a geospatial product. So we can then apply this to large areas without people having to consider all of the issues of processing large amounts of imagery. So I hope that's been of interest, and if anyone wants to follow our mailing list to find out more about it, you can just take a screen grab of this QR code, or it'll be in the presentation when you receive it. And then finally, here's my details and also an information account for if you just want to get in touch with the COP4N2K site there. Okay, thanks very much.
Brilliant. Thank you very much, Geoff. And thank you, Andy and Ben, for your really interesting presentations and sticking so well to time. That was a brilliant whistle-stop tour. As I said, we've just finished our presentations. If you do have a question for our panelists, please do ask or raise your hand if you'd like to ask them a question. As I said, the Q&A, it must have been very thorough because the Q&A has been quiet. But what I do have a question actually while we're kicking off. I do have a question for Andy myself. I said,
yes.
The National Use Efficiency Project sounds fascinating. It sounds like it's going to have real potential that will help a lot of people. You said you're still testing. When do you think it will go live? You said a few years?
So it's a 4-year project. I think we're now into the 2nd year. So it's got another couple of years to run. And at the end application, that which will be set up and run by ag analysts, is kind of being developed and rolled out now. So if you go to that website I showed you, I think they can start engaging people on using the calculator. But if in the meantime, I think they're still signing up farmers and farms who would like to be part of any of the trials. So if you're interested in participating, and you'll get help with things like soil nitrogen testing, leaf nitrogen testing and others. There's just some commitment to be made, access to land and data. But yeah, I think they're still looking for people to get involved. And hopefully the system will improve over the next couple of years. We've had the first full years of results, which are being analysed now. You saw some of the better ones in my example, and that they weren't all equally as good. And I should also say that as part of the project, that Assimila's part in this, because we're being funded publicly, we're going to make available our data for free for people to test and use on the side. So if you're interested in leaf area index data or F-cover or any of these products, and you want to try them, that's what we're going to launch at REAP tomorrow. But if you're not at REAP tomorrow and can't sign up there, just drop me a line. And for the period of the project, we're very happy to share data, and as long as people are willing to share their feedback, how good it is, because we're still learning how good these things are.
Brilliant. Thank you, Andy. And as I said, when I send the recording around of this webinar, I'll include your details in it so people can get in contact with you directly.
Thank you. That'd be great.
And as I said, in case anyone can't make it to REAP tomorrow. There was another question about basis points available. So yes, and Thomas has just answered that. Yes, 1 basis point. So if you have a basis number, I guess, Thomas, if you want to come back online, what's the best way for people to claim that? If you want to come back.
Yes, if they send me an email, my email's in the group, and we'll make sure it's logged.
Excellent. Okay.
My email's in the chat.
Oh yeah, thomas.wed@agritech.co.uk.
There is a form, but that's more applicable for live events. So yes, just send me an email.
Grand. I'll include your email as well, just so that people can still claim it tomorrow once this goes around. Perfect. Then, as I said, it seems pretty quiet. So if there's no other questions, we might be able to let people go early and get some of their day back. So Ben, are you happy to leave it there? Is there any other questions or points from the panelists?
Yeah, no, just to say thanks to Andy and Geoff for joining me in speaking, and hopefully we've given, albeit a very quick overview of satellite data, but hopefully given you an idea of sort of how there's so much data out there at the moment, it can almost be a bit overwhelming in terms of the number of satellites, the number of products, the specialist equipment that you need to sort of analyze that data. And it's becoming more and more that sort of companies such as Assimila and Specto Natura can sort of, well, bring this down to sort of to usable examples that people can get meaningful insights for. So I think it's been a great demonstration of that. So thanks very much to them.
Excellent. Okay, brilliant. Sorry, Andy,
throw all your data challenges at us. We like nothing more than to be challenged. One of the examples I showed, the company in question were hoping to verify things in the field from farmers using iPhones. And of course, farmers are too busy to do that. And they tried various remote sensing approaches and it wasn't working. So they were about to give up until we got involved. I know that's flag waving, but we do know what we're doing, and we like nothing more than a gnarly data problem. If you say, well, I've tried it and the cloud's too bad, or I don't trust the data, or is it accurate? Just throw your problems at us. We'd love to hear your feedback on what you've tried, what worked and what didn't work, because we'd like to know if we're wasting our time doing this. I don't think we are, because we're getting more and more inquiries now based on the way we're approaching it. It's very adaptable to different crops. I mean, I didn't even know about peas until Ben spoke about it. And that's another thing. I'd love to know what other crops, what kind of practices in horticulture would be amenable to this kind of work. So send us your feedback on challenges, and we'll be happy to answer them and help you out.
Brilliant. Thanks very much, Andy. Geoff, sorry, you have your hand raised.
Yeah, no, I was just going to add to that and support what both Ben and Andy have said. I think we're in a very different world of Earth observation than we were even a decade ago. I mean, the Sentinels were only launched in 2016, so we've not even had 10 years of those yet. And I think they, there's increases in cloud computing, processing power, data storage, and the sort of things we can do. I think we're in a new world, so you may have thought of Earth observation more than 10 years ago and discounted it, but yeah, please come and talk to us, see what your challenges are, and we may not be able to solve the exact problem, but we may be able to offer something that's complementary to what you're doing and maybe fix a different pain point. So yeah, please engage with us whenever you have issues and stuff. Great.
Brilliant. Good stuff. Right. I guess, as said, if there's no more questions, are we happy to leave it there? Everyone? Yeah. Perfect. All right. Thank you so much, everyone, for joining us. I hope you found that to be really informative. And we're going to leave it there and end the meeting. But thank you very much. Enjoy the rest of AgriTech Week. Enjoy the rest of REAP if you're going tomorrow. And see you again soon. Thanks. Bye.
Bye.
Thanks
Thank
all.
you. Bye.